Oops, alright, 17. Here's cylindrical garbage can of depth 3 feet and radius 1 foot. So here's my, oops, I did this again. Let's see here, sorry. It's going to take me just a quick second, but we're going to keep going. There we go. Okay, cylindrical garbage can. A depth of 3 feet. So this is 3 feet. And the radius is 1 foot. It fills with rainwater up to a depth of 2 feet. So here's my rainwater. 2 feet. Okay, how much work should be done to pump the water up to the top edge of the can? Okay, and we're going to use this value, so water weighs, we'll use this for the next few problems, 4 pounds per cubic foot. Okay, so we want to pump this up to the ledge so we can pump it out, right? Okay, well let's call this 0, and we're going to go down this way. This will be my x-axis. Okay, so what is the force? Well, I know my work is force times distance. Okay, so what's the force that's acting on this thin slice of water right there? Well, that's going to be 62.4 times the cubic feet. The cubic feet of this water, which is called that delta x, is going to be pi r squared times delta x. Right? That's the volume of that little thin slice. And then what is the work required to go from here all the way up and out? Okay, well the work for the slice would be the force times the distance it's going to move, which is going to be, that's x distance right there to get it out, right? This is my x-axis, but this is the distance x. So that's going to be the force, 62.4 times pi times delta x times the distance it goes out, right? Because this slice has to go up x units to get out of the, to be pumped out of the can. So then the total work will be adding all these up, adding all those slices up. And I'm adding them up and starting at 1 meter, and I'm going all the way down to 3. Right, because they said it started at 2 meters deep. So from 1 to 3. Okay. And if I do that, I should end up getting 784.1 foot-pounds. Alright, let's look at number 19. See if 19, it's the same, does use the same deal, or same water tank problem. So water is 62.4, what do we say, pounds per cubic foot. Okay, so we're going to do 19. Water tank is in the form of a right circular cylinder with a height of 20 feet, radius 6. If the tank is half full, find it. Oh, this is the same type of, exactly the same type of problem, isn't it? So I'm going to go ahead and not do that. Well, I'm going to go ahead and do this so you can check it. You should get an equation for work to be 0 to 10 of 62.4 pi times 4 squared x dx. Okay. This and the delta x, recall, come from my area, and then the x is the distance I'm pumping the water up. Right? Here's my slice, I'm pumping it up x units. So that's where that comes from, and if you do that, you should get 1,058,591 foot-pounds. So 1921 is the one that is very interesting, and we'll go ahead and look at that guy. Water cylinder is height of 10 feet, radius 4 is going to be pumped out. So let's draw 10 feet. Find the work required if the tank is full of water and it'll be pumped over the top. So the tank is full. Okay, so my work for the tank being full, right? One slice, like problem number 17. I'm going to be pumping from 0 to 10. Like I do one slice and then I integrate it to add them all up. It's going to be 62.4 pi times 4 squared, because the radius is 4, x dx. Okay, so are we all clear on where that comes from? Because the work it takes to move this slice out it's clear that you understand this is going to be given by the force to move this x units up. So it's going to be the force, which is 62.4 pounds per cubic foot times the cubic feet, pi times r squared times delta x, because that's the thickness, okay, times x. And then I integrate it to add up the work done for every slice, okay? And then as delta x goes to 0, that's the integral. Okay, so that's the first part. The tank is full of water. The water must be pumped to a height 5 feet above the top of the tank. Well, what you're going to need to do here, because see, we started our axis at 0 and then went down. Well, I want to pump it. I'm going to use this line right here. In fact, let me get rid of this. Okay, I'm going to start my axis up here at 0 now. And as I come down here, the top of the tank is at 5 and the bottom of the tank would be at 15. So where am I moving this slice is exactly the same. This is the work to do one slice. So now where am I moving this slice of water to? All the way up to 0, right? So I'm moving it from down here, so this would be x. See, I moved my axis because I want the distance from where I end to my slice to still be x. So that's A. So for part B then, the work is going to be from 0 to 15. I'm sorry, 0. Where am I moving it from? It's going from 5 to 15 of 62.4 pi times 4 squared x dx. It's the same amount for this slice, right? The work is still this number right here, because x is for my slice all the way up to the top. But now I'm taking the slices from 5 down to 15 and pumping them out. Okay, and then C, the depth of the water of the tank is 8 feet and the water must be pumped over the top. Well, this is just going back to the original type of problem where this is 0, this is 10. It's 8 feet deep. Okay, so I'm going to find the work there is going to be the integral from 2 to 10 of my slice, which is 62.4 pi times 4 squared x dx. Okay, so if you do that, you get 150,555 foot-pounds. And if you do this one, I'm sorry I didn't write it earlier, 313,657 foot-pounds. And A, did I tell you what A was? 156, sorry. 156, 828 foot-pound. Okay. That's a lot in one problem, and that's pretty fast for that problem. But if you understand this, then I hope all these make sense. Okay, there you go.